Hi, everyone. Whoa, this is loud. Okay. Before your lecture gets started, we just wanted to announce a resource that you guys have access to here. Hi, I'm Varsha. Do you mind turning the music? Thank you. Okay. Hi, I'm Varsha. I'm one of your discussion TAs, and I'm also the co-coordinator of CSM EE16A.
Hi, I'm Yanin. I'm the other EE16A coord.
So, if you haven't heard of CSM, Computer Science Mentors is a volunteer organization that holds small group tutoring sections every week with about 4 to 6 students for EE16A and other courses. It will help you, if you sign up for one of these sections, it'll help you not only get a better understanding of the material, but also fix some of the concepts that you might not have completely understood and other things like that. Sign-ups will be opening
next week, maybe not exactly the 9/3, but keep a lookout on Piazza and it'll be up. And if you are interested in getting more info, you can visit our website, csm.berkeley.edu, or shoot us an email at mentors@berkeley.edu. And this doesn't require an application or anything. You just need to be there to sign up for the spaces that are open.
So we have over 200 mentors in CSM, and about 1,000 students sign up every semester. So please sign up. If you think it'll be a useful resource, it definitely will. And we always have space. So yeah, sometimes. Yeah. Thank you.
Thank you. Okay, 9:40, time to get started with lecture. Once again, as you can see, there are many empty seats. So for everyone who on the first day of lecture was not able to get a seat, all of the people who are watching on the webcast, there's many empty seats. If you would like to be in lecture, please do take the opportunity. I really encourage all of the first years and all of the junior transfers, especially to be in lecture. You can think of it as, almost mandatory. Just a couple of reminders. We have a no tech policy in class. If your neighbor has forgotten this policy, please remind them. If your neighbor is using a notepad to take notes, please, make sure that you're not being disturbed. If you're being bothered by this, please turn it off. I support writing notes with a pen. If you want to do this, you can come talk to me after office hours and in office hours and have special permission to do so. Typing up notes in class is not something we would like to encourage. If you have some special requirements that make you want to do this, please come talk to me. Same goes for cell phones. So please, no technology in class. Okay. Next reminder, I got a bunch of questions about, do we need to read the notes? Yes, please read the notes. They will help you. Lecture will be covering things in a slightly different way from the notes, and the idea is that by having lecture and the notes and discussion, you will get multiple different perspectives on the material, and and which will help you develop fluency in going back and forth from one way of thinking to another. Homework 1 will be due tomorrow, Friday at midnight. Homework 2 will be released tomorrow. It will again be due in a week. Please don't forget to submit your homework. Hopefully everyone got practice in how to submit their homework during homework 0. Finally, there are 2 discussion sections every week. There is a Monday discussion section and a Wednesday discussion section. So this week there was a discussion 1A on Mondays and a discussion 1B on Wednesdays. You are expected to attend 1 discussion on Monday and 1 discussion on Wednesday. It's not either Monday or Wednesday. Monday discussion is between the Thursday and the Tuesday lecture. Wednesday discussion between the Tuesday and the Thursday lecture. That's how the days of the week work. So different discussions will cover different parts of the material. Please attend 1 each. You do not have to go to the same discussion on Monday and Wednesday. You can go at different times, but choose 1 discussion on Monday and 1 discussion on Wednesday. In response to the fact that there's been a lot of demand for certain discussion slots and certain types of discussions, we will be including a couple of extra freshman-oriented discussions and possibly some other discussions for more senior students as well. Check the website tomorrow, and the new discussion schedule will be posted. There will also be a post made on Piazza. So if you've been going to a discussion section where there are no seats, there are plenty of open seats in other discussions. Check the poll on Piazza. Please go to a discussion where you actually have a chance to talk to the TA. Okay, with that, let us get started with lecture. So, what I'm going to be covering today, we are going to be talking about matrix vector multiplication. And we're going to be thinking about this as kind of a shorthand for systems of linear equations. And then we're going to be talking about different interpretations of matrix vector multiplication. So we're going to go outside the realm of purely solving systems of linear equations and think a little bit about what these things mean more abstractly and how you can use them to think about design and different kinds of systems. And finally, we'll be talking about the concept of linear independence and dependence. So last lecture, we talked about this concept of Gaussian elimination. Right? And what is Gaussian elimination? Gaussian elimination is this algorithm that we used when we want to find solutions to systems of linear equations, right? So let's say we have a large system of linear equations, say a11x1 plus a12x2 plus a1n xn equal to b1, and then a21x1 plus a22x2 plus a2n xn equal to b2, so on and so forth. And let's say we have m equations, a m1x1, m2x2 plus a mn xn equal to bn. So when I say these ... dots here, that means fill in the obvious pattern. So what would be the third term here? Exactly. So we haven't really started using these indices and this kind of notation so much yet, but in this lecture we're going to start transitioning into using more and more notation so that you can be familiar with it. So that when you encounter it in some other class or in another textbook, you'll be able to follow along. So m equations means there's m rows here. And if I wanted to write this out as an augmented matrix, I could write it out the following way, right? We discussed this. Can someone call out these entries to me? A11, A12, all the way up to A1n, and then so on and so forth, up to A M1, all the way up to A mn, And then this bar to remind us that these b's are slightly different, b1, b2, all the way up to bn. And this is what we call the augmented matrix. Right? Yes, question, white t-shirt. Yes, great point, thank you. Did everyone understand what was just said? The question was, is this bm or bn? And it should be indeed bm. Why? Because how many equations do we have? We have m equations, right? So these should both be bm. So we have m equations and n variables. Everyone catch that? Thanks for pointing it out. Other question? Okay. Good. So, one of the terms we used last time when we were discussing this was the term linear combination. And I just wanted to define this. What is a linear combination? A linear combination is basically when you take a bunch of terms and multiply them by a constant and add them. So for example, this equation here, a11x1 plus a12x2 plus a1 and xn, is a linear combination of the variables x1, x2, and xn. Okay? If the x1, x2, xn were constants and the a11, a12, a13 were unknowns, then we could think of it as a linear combination of the a11, a12, a1n variables. You can interpret it in both ways depending on what is a constant and what you know and what you don't know. Either way, this is called a linear combination. So like, if you want to make a linear combination of the variables x and y, 2x plus 3y is a linear combination of 2x of x and y. But there's many, many linear combinations that you can make of x and y. Is this clear what when I say linear combination, what I mean? Any questions about that? Okay, good. So now that we know this, what did we do with this augmented matrix? What we wanted to do with it was we used Gaussian elimination to transform it to something, right? And we transformed it into a particular format. We tried to transform it into something that was upper triangular in nature, right? So we wanted it to be something where there's a bunch of stuff here that is non-zero above the diagonal, and then below the diagonal, there are all these zeros, right? This is what we wanted to do. And here you would have some element, let's call this alpha 1, alpha 2, alpha 3, all the way up to alpha m. And we defined what these alpha m's are. Once we get into this upper triangular form, once we have all of these zeros versus all of these non-zeros up here, we called these alphas something, right? These alphas are elements on the diagonal in upper triangular form. And we define these to be pivots. All of these elements that are on the diagonal, when you have basically a row that is of the form 0, 0, 0, something on the diagonal. So diagonal is basically, when you look at this matrix, what are the elements on the diagonal? Here, it's A11, A22, A33, A44. So for a square matrix, which is the case that you have when m is equal to n, which is what we've been talking about, all of these AII type entries are the entries along the diagonal. It's just basically when you draw the square and you draw the diagonal, the obvious thing that you would think of as the diagonal is the diagonal. So up until yesterday, we were really focusing in all of our examples on the case m is equal to n, right? We are thinking about the number of equations is equal to the number of unknowns. right? This is the kind of setup that we've largely been looking at. And in this case, what did we find? We found out some stopping conditions for Gaussian elimination, right? What were the stopping conditions that we figured out for Gaussian elimination? We looked at 3 cases. Does everyone remember what were the 3 stopping conditions that we discussed for Gaussian elimination? Take a minute and just talk to your neighbor and remind yourself of what these stopping conditions were. Make sure that, you haven't forgotten. Check with your neighbor that you remember the right thing. Okay, does anyone want to volunteer to tell me what one of the stopping conditions was? Or all 3 of them for that matter. Any volunteers? Yeah. A row of zeros. Good. We all remembered that if there's a row of zeros, something is going on, right? So basically, first way you stop is if you get a row that is 0, 0, 0, 0, something, and then there's kind of 2 cases, right? I have a row of zeros, and I have here a b that is not equal to 0, right? If I get a row of zeros, and then something on the right-hand side of the line that is non-zero, what does that mean? No solutions, right? And why is it no solutions? Because 0 times x plus 0 times y plus 0 times z, what is this always going to be equal to? 0. So you can never achieve something that is non-zero there, right? So this is a big way of saying that you have no solutions. Let me just finish one point. And then we also talked about this in terms of pivots, right? So if you get a row of zeros, that means in your upper triangular form, if you have a row of zeros, that means you also have a 0 pivot. So another way of thinking about it is to say, what happens if you have a 0 pivot? Again, we get into this situation where we have, we need to look out for things and we get this no solution situation. But what is the other way in which you can get a row of all zeros? What's the other case? You could actually have b equal to 0 here, right? And if you get in a square matrix, a set of, in the upper triangular form, you get basically a row of all zeros and the right-hand side is also equal to 0. What does this mean? Infinite solutions. And does someone want to tell me why this means infinite solutions? Yeah.
So that means you have 0x1 plus 0y1, x2 right plus 0x7 would be 0. So then you can plug in anything to make it equal to 0.
Exactly, right? If you have 0x plus 0y equal to 0, this equation is true for all x and y. It doesn't matter what x and y I choose, so I have some extra degrees of freedom. There's more than one solution. Exactly. Exactly. There's more than one solution. And finally, we had a third stopping condition, right? Which is kind of the usual case or the normal case. So, anyone? What was the third stopping condition? Yeah. You have ones along the diagonal. Yeah. So third stopping condition is ones along the diagonal. So I'm going to write this in terms of rows since we're talking about rows. But you get rows that are 0, 0, 0, A, or A, I equal to 1, and then 0, 0, 0, or something stuff. And then, okay, this did not look pretty. Let us write that again. 0, 0, 0. Then I get a 1. This is in position I, comma, I. And then I have some stuff here. This may be 0. This may be non-zero, right? This may be some, this C, D, E, so on and so forth. And then I get a B. Right? So if every single one of my rows is such that I have basically a non-zero element in the diagonal, and then I have something else, then basically I have this exact nice upper triangular form. What if I had something here that was not a 1, but was like 13? Is this a problem? No, what would you do? You could just divide by 13, right? So saying that you have a 1 here, or saying just that you have a non-zero entry there, is good enough. And if you look at this in upper triangular form, if you want to look at the last row should be of this format: 0, 0, 0, all zeros, except for this last entry, which should be, let's say, call it 1, equal to something, right? If I get the last row to be like this, then that also means that, basically, again, this is the diagonal entry in the last row. This means that I am in the situation, what situation? No solutions, infinite solutions? One solution, or a unique solution. Okay? So, is everyone clear on this? Any questions? Yeah. So in a square matrix, so basically when you have n equations and n unknowns, if you get a row of zeros, what that necessarily means is that you have some redundant equations. And exactly this is what the rest of the lecture is going to build on a little bit. So if you have an n by n matrix, if you get a row of zeros, you will have basically a no solution or an infinite solution situation. When you get a row of zeros, again, remember, we're trying to make things into upper triangular form, right? So if you see a row of zeros, the swapping rule will dictate that you move that row of zeros all the way to the bottom, right? Basically, because what is our upper triangular form? Our upper triangular form is such that you want one extra 0 in every row, right? So when you get a row of all zeros, automatically your rules are going to say move it all the way to the bottom. You might get infinite solutions or no solutions with that row of zeros. This will change slightly when you have, m not equal to n, and we're going to talk exactly about that a little bit in like 30 seconds. Question, yeah?
Does having a row of zeros always mean that there will be either infinite solutions or no solutions, or might it mean that we simply need more information, like in the case of the tomography problem?
Great question. The question was, does a row of zeros always mean that you have no solutions or infinite solutions, or might you need more information? So, how many people were in discussion yesterday? How many people remember Nara and Cody? So, does someone want to tell me, or do you want to tell me what Nara and Cody did when they found out they had some measurements, they had a matrix, but they basically got a row of zeros, right? What did Nara and Cody do?
They took that fifth measurement, which used percentages as opposed to complete wallpapered light, and that gave them that diagonal they needed to find a good system of equations.
Exactly, right? So you're basically saying that sometimes when you find a row of zeros, and this row of zeros is leading you to believe that there's infinitely many solutions, what you can do is you can find another measurement that will then help you resolve the situation. It will help you actually come to a unique solution. On the other hand, there might be a case where you have a row of zeros equal to something not 0. In this case, things are a little bit more tricky because it's saying that somehow the equations you have are inconsistent. Now, in a real engineering scenario, you might try and, drop one of the equations, swap it out with another equation. These are getting to slightly more complicated things, which we will be coming to in the second part of 16A. So just like hang on for a couple of weeks. We'll start talking about noise, and all of these questions will get answered. Yes, question?
So it's not the case that the second condition is a true stopping condition, so there could be no solution as well?
It's not the case that the second condition is a true stopping condition. No, if you get in a square matrix where you have n equations and n unknowns, if you get a row of zeros equal to 0, you will have infinite solutions. If you have two rows above that were contradicting each other. So under Gaussian elimination, you will hit the row of zeros first if you follow the algorithm. Will you have a row of... you're going to... If you hit a row of zeros in a set of equations, basically, because you haven't used all of the equations yet, right? If you hit a row of zeros, that means that everything up to now has already been used, and there's already a redundancy there. So if you were to find inconsistency, it would come lower down. But these questions become more relevant when you're thinking about like different numbers of equations and different numbers of unknowns, and I'll do an example that will hopefully clarify exactly this question. Okay, so let's quickly think about this case where m is greater than n. So what this means is that there's more equations than there are unknowns. So what if you have the following situation? You have 1, 1, and then 2, and then 2, 2, and then 4, and then 3, 2, and then 5. Can someone take a minute and quickly do Gaussian elimination on this? So, what is the natural thing to do? I'm going to take row 2 minus 2 times row 1, right? Everyone with me? Wow, everyone's really either asleep or really doesn't like their neighbors. Both are sad. I prefer asleep. What do you get? 0, 0, and 0. So what do you conclude in this case? Why is this the case? Can we conclude from here that there is infinitely many solutions? No, we can't, right? So what is the natural thing to do now? What you do is you swap the rows, right? Why did this happen? It's because basically I told you, x1 is 1. One equation. And I told you, by the way, did you know x1 is 1? Another equation. And it's saying, even if I give you the same information over and over again, it doesn't count as new information. It's the same equation repeated. So now this gives me 3, 2, 5, 0, 0, 0. And now what happens when I take the next step? What do I get? I get 1, 1, 2, and then what? 0, -1, and -1. 0, 0, 0. So now what do I have here? I have basically a square matrix like situation up here, and this is my upper triangular matrix right in there, right? This is my triangle. Okay? Does this make sense? What we just did here? Okay. What if now we had another situation which was 1, 1, 2, 2, 2, 5, and 3, 2, 5. Try the next example. Talk to your neighbor. What's going on? Okay. So, does someone want to tell me, shout out, what is the next step? What happens when you perform Gaussian elimination? 1, 1, 2, and then what do I get? 0, 1, 3, 2, 5. Right? Now if I was to continue to do Gaussian elimination, just to be, very careful, what would I get? I would get 1, 1, 2. Then I would get 3, 2, 5. And I would get 0, 0, 1. And then I would get 1, 1, 2, 0, minus 1, and 0, 0, 1. So here, when we look at this form, what do we see? We see this row, right? Even though we have this structure up here, what is this last row telling us? We've moved the row of all zeros all the way to the bottom, and we still have this 0, 0, 0, non-zero row. What is this telling us? No solution. There's something inconsistent, right? Because I can't have basically one, like x plus y equal to 2 and 2x plus 2y equal to 5, right? These two equations are going to be inconsistent with each other. Does everyone see that? Yeah, question. In the case that you have, so basically you cannot have a solution that satisfies all of the equations you are given. You can choose, some subset of the equations, and you might be able to solve those, but you won't be able to find variables that simultaneously satisfy all of the equations. It's like saying, if I give you 3 different lines, in a plane, you can't guarantee that all of them will pass through the same point. You might have multiple points of intersection. Yeah? In the first one? In the first one, I couldn't say that it was infinite solutions immediately because I had more constraints on my variables, right? So, in addition to having the 1, 1, 2, so basically every time, every format, right, I can interpret this as one set of constraints. I can say when I do Gaussian elimination, I'm saying here is an equivalent set of constraints. So here in this equivalent set of constraints, I basically said that this middle constraint is a non-constraint, but that doesn't mean that my other 2 constraints have gone away. So I still have these 2 constraints, and I still need to find x and y that satisfy those 2. There is no z variable here, right? There's only 2 variables. Yeah, question. So in this case, when I wanted to solve for x and y here, where there does exist a solution, so I have minus 1 y equal to minus 1, right? That's what this means. So what does that mean y is equal to? 1. So y is equal to 1, and then I substitute this gives me y is equal to 1. And here I have x plus y equal to 2. If y is equal to 1, what is x equal to? 1. So I can solve it back exactly the same way as I would have. Question? What if you try subtracting row 3 from row 2 at the beginning? It's a great exercise. Try subtracting row 3 from row 2 and see what happens. Come talk to me in office hours if you can't figure it out. Yeah.
So is it fair to say that when you get multiple stopping conditions in a linear matrix, that the order of importance is, no solution, then unique solution, and then
Yes, you should first look for the case that there's no solutions, then infinite solutions, then unique solutions. Yeah. Do you want me to repeat the argument for the second matrix? Is that okay? How to interpret it by using the zero pivot. So basically here, that's a very good question. How do you interpret this by using the zero pivot? So here it's a little bit tricky because when we're looking at the diagonal of this matrix, because it's not a square matrix, there's not exactly a clean diagonal, right? So the pivots are most important in the case of square matrices. In this case, basically, because you have this zero here, which is at the end of the last row, is playing the role of this zero pivot. Yeah, but I really recommend, so the question is about how do you connect pivots to rows of zeros. In the case where you have a number of rows that is bigger than the number of variables, or number of equations that is more than the number of variables, I really recommend just think about it in terms of the rows of zeros. That'll be easier than trying to map it to the pivots, which are better defined for a square matrix when you have things on the diagonal. I think it's a really good way of thinking about things to try and map things back and forth. But for now, just think about this, just think about it in the row interpretation.
So basically, so whenever you do, when you do row reductions, you have to show R2 minus 2R1, show what you're doing, like that.
When you're writing out problems in homework, yes, especially at the beginning, make sure you write out the operations that you're doing. It'll help you kind of learn the process of Gaussian elimination. You can write it out. Just write a quick note. That way people know what you're doing. Exactly. Teaching is always the best way of learning. When you can try and teach something to someone, it always means that you learn the stuff better. That's why it's so awesome to be on course staff. Last question.
Is there any reason to continue the Gaussian elimination after you reach the no solution for the part 2 and step 2?
Here? Yes, because by Gaussian elimination, the rules of Gaussian elimination say that the rows of 0 should be at the bottom. Right? You have not yet gotten to this case where you have the first element of the first row is non-zero, and the second element of the second row is non-zero, and the third element of the third row is non-zero. So you want to have that format. That is what is called the upper triangular format, right? And this guy is not in that format. So you haven't reached a stopping condition for Gaussian elimination yet. First, you have to get it into the upper triangle. Yes, but because, again, remember, you want to teach a computer to algorithmically do it. You are able to see this because you're using your intuition and you know some algebra, but when you're programming a computer, you need to be very precise. Okay, last question for real this time.
I forget what this means, but on the bottom row, what if the 1 were switched with a 0? So you had, say, 0, 1,
that would be a completely different matrix, a completely different setup. You would not be able to get that from this initial augmented matrix configuration. You can try to back calculate, see what would give you that. Try to work it out. If you can't make sense of it, come to office hours. Okay, let's move on because we have a lot of ground to cover and we are behind. Okay, so with this now, I want to go back to thinking about the n by n case. But I just wanted to point something out here. Here, when we're choosing what row operations to do, when we're choosing what to subtract from what, which row to add to the other, are we ever looking at the values of the b's? Look at here. The first step we did in the Gaussian elimination here. Did the fact that here b had a 5 in it and here b had a 4 in it, did it change the operation we did? No, right? The operations we did only depended on the aij coefficients, right? And the outcome, whether or not, how many solutions we had, that depended on the b's. But the process of Gaussian elimination only depends on what values are in the aij's, right? So now, let's go back to, again, the n by n case, so we can talk about things in terms of pivots. And let's say I just give you this matrix, A11, A12, A1n, AM1, AMN. And I don't tell you the b vector. There is some b vector, but I just don't tell it to you. Can you tell me if you're going to get a row of zeros or not? I'm not asking you to tell me if you have 0 solutions or infinite solutions. I'm just asking you to tell me if you're going to get a row of zeros. And actually, sorry, I want this to be a square matrix, so let's make this n. And since this doesn't look square, let's redraw this. N by n case. A11, A12, A1n, AN1, ANN. So there's a clear diagonal. So can you tell me, just looking at this matrix, if I just tell you the values of the A's and I don't tell you the values of the B's, can you tell me if you're going to end up with a row of zeros? Yes, right? Does everyone see this? Okay, good. So now what this is saying is, like, when we think about these A's, what are these A's, right? These A's are representing A11 x1 plus A12 x2. What are these A's representing? For example, in the tomography situation, right? Yeah? They're representing coefficients in a linear combination. Great answer. But if we think about things, kind of think really about you're the person tasked with designing, how you're going to shine light. Or think about Cody and Nara. Cody and Nara are choosing which measurements to take. What the A's are representing are what in this case? Yeah, behind you. Yeah. Very good. You said exactly the word that I was hoping someone would say, is you're talking about the measurement, right? You're talking about the design of the experiment. When you're choosing the A's, this is the experiment you're setting up. The A's, for example, are saying, am I going to shine light straight through? Remember our 4x4 grid or 2x2 grid from the first lecture? X1, X2, X3, X4? The tomography example? This is saying, am I going to shine light straight, or am I going to shine it vertical, or am I going to shine it diagonal, right? These choices of straight versus diagonal versus vertical versus horizontal, this is what the A's are representing. Is this clear to everyone? So this is basically your experimental design. And what are the B vectors? or the B vector, I guess, just. This is the measurement you're getting out. So you, the engineer, chooses the A matrix, right? Who chooses the B matrix? Or the B vector, sorry. Nature, right? Nature is choosing this. So this is a really important thing to realize when we're talking about any kind of engineering. What's this saying? The fact that you can figure out whether or not you're going to have a unique solution just by looking at the A matrix means you can reason about the fact, or you can reason about the question, well, is my tomography machine, are my measurements going to work without actually building the machine? Right? You will know if you're doomed to failure before you actually collect any data in some cases. And this is really important because, building the entire tomography machine is pretty expensive. You can't always do this. So what this A matrix is doing is it's saying that, you can actually reason about this. And this is the reason that we introduce this notation, essentially, which is this matrix vector multiplication notation. Where we have, basically, this is our A matrix. Times x1 up to xn is equal to and we write this as A, matrix A. We will use a capital letter to denote matrices, times x. X is a vector, which we will show with this little arrow on top, equal to B. So this is capital letter. This has this arrow. Is everyone clear? So when we're talking about this, when we talk about matrix vector multiplication and using it to represent a system of equations, really all we're doing is nothing, we're just using notation. It's just a way of representing things. There's nothing particularly fancy or magical that is happening here. Yeah, question at the back. What exactly can you tell from just the A matrix? Does someone want to answer that question? Yeah? Whether you have a unique solution or not, right? You can tell from the A matrix whether or not you have a unique solution. So the question is, what can you tell from the A matrix? And can you tell, basically, does the B entry matter? So if you have a row of zeros, right? What are the two options that you have if you have a row of zeros? You either have infinite number of solutions or you have no solutions. Can you have unique solution when you have a row of zeros? Do you need to know the value of the B vector to figure out if you have a row of zeros? Got it? Okay, good. So now, I want to just talk a little bit about this. So when we write this out into, in the equation form, this is just one notation. But what does this A11 multiply? X1. Okay? And here, let me write out this guy. A12, A21, A22. And what does A12 multiply? X2. Right? And what about this last guy, A1n? Xn. Okay? And then what about A21? X1. And what about A22? X2. Okay. And what about, let's say, ANN? XN. So are you guys seeing a pattern here on what's going on? What is the first column of the matrix? What is the variable that is associated with? X1. And the second column is associated with the second variable. And the third column is associated with the third variable. And there's this structure here that we're seeing that is not, that was not something we were like explicitly thinking about when we constructed this matrix. We basically we just took these equations and we did the lazy thing of dropping all of the variables, right? We just said, let's not write the variables multiple times. But there's this structure that is starting to kind of emerge. And so what we're seeing is that there's something happening about each of these columns, right? And if we were to think about what does this column mean? I want to think about columns of A. I'm going to call this A1 as a vector, and I'm going to draw this column, A11, A21, AN1, which is the first column of A. And then you have A2, which is the second column, so on and so forth. So what do you think these columns represent? We know what the rows represent. The rows represent basically each measurement, right? It's each experiment. It's shining light through the first horizontal, then it's shining light through the second horizontal, then it's shining light through the diagonal. What about the columns? Take a minute and, talk to each other. See what you can come up with and what do these columns mean? Can we interpret them somehow? Okay, any ideas on what the columns might mean? Yeah? Yeah, exactly. What is being pointed out is that, all of these are associated with the same variable. You're trying to take different measurements of the same variable. So let me give you a little bit of an example. What if our A matrix was the following? 100, 1, 1, 1, 100, 1, 1, 1, 100. So this is the first experiment, right? What is this saying? It's saying that X1 matters a lot more in the outcome of the first experiment than X2 and X3, right? We're putting this weight of 100 on X1 and only weights of 1 and 1 on X2 and X3. Now what about the second row? What is the most important variable when you're doing this second row experiment? X2. And the last one is X3. What if in the first row, instead of having this, I change this to also being 100? What are the most important variables in the first row? X1 and X3, right? So we're saying when we're taking this measurement, how much does the value of this variable affect what is going to happen? So it's like measuring the influence somehow. Or it's saying, how sensitive is my measurement to a particular unknown? So these columns basically are kind of representing this sensitivity of your experiment. Is this making sense to people? Like, we're trying to go beyond just the mechanics of what, these matrices are, and trying to really think about physical interpretations for what they mean. Why do we want to do this? because then when you're actually trying to debug your tomography machine, you will have some physical intuition as to what might be going wrong. Questions, comments? Yeah, at the back. It's not measuring sensitivity. The question was, can you talk again about the sensitivity interpretation? And what we're saying is that we want to understand the relative importance of x1, for example. And so let's say here, let's look at 1 times x1 plus 100 times x2 plus 1 times x3. Okay? And now, in the case that x2 is 0, right? What is this? If x2 is 0, and x1 and x3 are both 1, then we get this equation is basically equal to 2, right? If I basically put in the value for a vector x as 1, 0, 1, then I get this thing is equal to 2. But what if I made a very slight change? Instead of the 0, I made a 1. So what if x was 1, 1, 1, right? Then 1 times x1 plus 100 times x2 plus 1 times x3 is equal to 102, right? So suddenly a small change in x2 led to a very big change in our measurement. And so because we had this high weight on x2, this particular experiment, every row, remember, of our matrix represents an experiment, this particular experiment was very sensitive to the value of x2. That's the only thing I'm trying to communicate. Is that clear to everyone? Make sense? Great. Okay. So now, what I want to point out is basically, we started this matrix notation by really focusing on the rows. We constructed it from the rows. What I'm trying to say to you is look, there's something interesting about the columns too. Let's not ignore the columns. Let's have equal opportunity for columns and for rows. So now, I just want to quickly introduce two pieces of notation. So we have scalar vector multiplication. And what is this? This is basically saying that if I have some constant times a vector x, which is equal to some constant c times x1 all the way up to xn, the vector I get out is basically cx1 up to cxn, right? So if I have vector 1, 1, and I multiply it by 2, what do I get? 2, 2, right? This is all that this is saying. Just wanted to make this clear. Second point I wanted to introduce, vector addition. So if I have a vector A plus vector B, what is this? This is equal to, let's say, A1, A2, AN plus B1, B2, Bn. And this we're defining. Here also we're defining this to be equal to A1 plus B1, A2 plus B2, all the way up to AN plus Bn. And how many people have heard the word commutative before? Some people have heard, right? Commutativity of addition is something we take for granted for real numbers. What does commutativity mean? Commutative means 2 plus 3 is equal to 3 plus 2. It doesn't matter what order you add things in. And this is one of the properties of vector addition. So A plus B is equal to B plus A. And the second property that we are going to need is associativity. How many people have heard associative before? What is associative? It means that 2 plus 3 plus 4, you can do 2 plus 3 first and then add 4, or you can do 3 plus 4 first and then add 2. The order of operations doesn't matter. So the same is true for vectors. A plus B plus C is equal to A plus B plus C. There's a couple of other properties of vector addition, including, additive inverses and so on. Read the notes for this. For those of you who are looking for extra credit opportunities, I would very happily award extra credit to someone who was to make a cool IPython demo that demonstrates the concepts of vector multiplication, vector scalar multiplication, as well as commutativity and associativity. If you have a cool demo that you want to make, it would be a great idea for extra credit. Come talk to me if you're interested in building something like that. Okay, but we have these basic definitions. Anyone have any questions about this? No? Okay, good. So with this now, I want to move into talking about another thing. Oh, you can't see this. So, what happens if the number of equations is 1? What is m equal to 1? What does matrix vector multiplication look like when your m is equal to 1? In this case, you have a1, a2, a11, a12, a1m times x1, a1n, x1 up to xn equal to, let's say, b1. Right? When we have something like this, we have basically one row, one experiment, and all of these measurements. What does this look like? I think somewhere in kindergarten or maybe first grade, you learn this concept of sleeping lines and standing lines. So there's the lines that are flat and the lines that are tall and long. So these are sleeping vectors and standing vectors. So this looks awfully like this guy, right? It's basically like a vector, but it's put horizontally instead of vertically. So this is a row vector, and this is a column vector. And what is this saying? This is basically defining what we will talk a little bit more about later, but basically using this idea, using the definition of matrix vector multiplication that we already have, we're seeing implicitly there's an element of a vector multiplication, or an inner product that is also being talked about. And so we basically, using our interpretation, right? Using our interpretation of this, how do we write this out as an equation? What multiplies what? a11 x1 plus a12 x2 plus a1n xn, right? So when you see notation like this, what is it saying? What did we define at the beginning of class? We defined linear combinations, right? So this is just a way of representing a linear combination of the different components of the vector x. Is that clear to everyone? And then when we do matrix vector multiplication, it's just taking multiple experiments or multiple linear combinations. So you're stacking each of these rows on top of each other. So all of these things are very, very connected. And if you start thinking about, vector multiplication and matrix vector multiplication and all of these things as kind of different versions of the same thing, and start understanding how they're connected and why they're representing this system of linear equations, learning and memorizing all of these things will become much easier. And once we start talking about matrix multiplication, things can sometimes get tricky. But if you all keep trying to remember, what are we trying to do? What is the interpretation? If you keep reminding of yourself, what the notation means physically, you'll be better off. Okay, last thing that I introduced. So now finally we have some time to talk about the column view of matrix vector multiplication. So we've talked about why columns are important. So now I want to just quickly shift to using this IPython notebook. Can everyone see this? So this is a demo that was made by one of your ASCs, Lily Bhattacharjee. Her picture is up here. She did a great job. So if you like this demo, please give her a big hand at the end, or post to Piazza, call out for her. Thank you to Lily for helping me make this. So what we want to do here in this demo is we want to try and really play with the interpretation of matrix vector multiplication. So what Lily is doing here is she's basically building a matrix. This is a matrix A. And this part, can everyone see this, or is it too small to read at the back? Zoom in? Okay. Can people read it now? Yeah? Thumbs up at the back? Yeah. Okay. Everyone see this matrix? The columns are 5, 7, 4, 2, 2, 3, 8, 4, 1. Yeah? Okay. Does anyone want to pick a vector that we want to multiply, that we want to use for multiplication? I have 1, 3, 2, but we can pick whatever you want. I heard 9, 1, 3. Okay. So let's run this. And this prod, this np dot dot, is just doing a multiplication. So this gives you basically this dot product, right? And now what this is doing here is it's just plotting this vector, 71, 77, 42 in 3D space, right? So it's a super cool demo. You can actually view this vector, right? Everyone see that? Okay. Now, this is just saying what that is. Now, what Lily is doing here is, instead of doing this matrix vector multiplication, she's saying, let's focus on the columns of A. So here, A1 is the first column of A. Does everyone see that? Vector A2 is the second column. Vector A3 is the third column. Everyone with me? And here, x0 is the first component of x, x1 is the second component of x, x2 is the third component of x. Everyone see what the components of x are? Basically, they're 9, 1, and 3. So what she's doing is she's saying, let's focus on the columns. We've been talking about the rows, let's focus on the columns. And she's saying, let us multiply this scalar x0 by this vector A1. So x0 times A1. And then she's saying, let's take x1 times A2 and x2 times A3. And get these intermediate vectors. And then she's saying, let's take this intermediate vector 1 plus intermediate vector 2 plus intermediate vector 3. And what comes out? Does this look familiar? What just happened? What did we calculate up here? What was our A times x? 71, 77, 42. What was the sum of our three x0 times A1, x1 times A2, and x2 times A3? the same thing. So if I look at this intermediate vector 1, I get basically this is x naught times a1 is this value. What is intermediate vector 2? Is x1 times a2. And I forgot to write out intermediate value 3, but we can just do this. What is intermediate value 3? Intermediate vector 3 is 24, 12, 3. And now what this is doing is it's just saying, let's plot these vectors. So if you go, intermediate vector 1 goes from here to here. Intermediate vector 2 takes you from here to here. Intermediate vector 3 takes you from here to here. Does everyone see these 3 blue arrows? And what is that exactly equal to? What is the orange arrow is basically the sum of these things. And now what she's plotting here is basically look at first this green arrow, which is the A times X, the matrix A times the vector X, and compare it to the sums of these 3 vectors. And it turns out that these are actually exactly the same. And what you see here, the reason you only see one arrow is because the orange arrow is exactly below the green arrow. So what we're saying is that we want to take this column perspective, and what is this demo suggesting? It's suggesting the following claim. Claim, matrix A times vector X is equal to column 1 times the first component of X plus column 2 times the second component of X plus column 3 times the third component of X. Right? Oh, sorry. So, how many people think that that demo was a fluke? How many think that, like, Lily pulled a trick in making this demo? Trick? I see 1 vote for trick, 2 votes for trick. How many people think that there's something going on here, underlying, that we want to understand? It's pretty cool, right? We started by looking at things in terms of rows, but now we're starting to look at these things in terms of the columns of A, and we're starting to find some structure. So before we go into that, I just want everyone to give a big hand to Lily, because I think this is a great demo. Thank you, Lily. But now, let's quickly try and come back to this in the last bit of lecture. We have some time to be able to actually play with this. So, what we saw here is we had this A times this vector X. We saw this product, and we got vector A, the first column times x1, second column times x2, third column times x3. Okay? So now what we're going to do is we're going to do like basically your first ever proof in 16A. And for this, I want to have some help. So what is A1? A1, can someone tell me? Call it out. A11, A21, A31, right? Let's say it's just a 3 by 3 matrix, like the example. And what is x1 times A1? x1, A11, x1, A21, x1, A31, right? And what about x2 times A2? x2 times A12, x2 times A22, x2 times A32. And what is x3 times A3? Is x3 times A13, x3 times A23, x3 times A33. So it's basically saying, let me consider these components. Remember we talked about the columns are like these sensitivity per experiment, right? And so I'm saying, let me take all of the sensitivities for x1 and put them together in a column vector. And all of the sensitivities for x2 and put them together in the column vector. The impact of x1 is this first column. The impact of x2 is the second column. The impact of x3 is the third column. Yeah, question? Oh, sorry, that's a typo. Yes, thank you. This should be an x1. Thank you for catching that typo. Does everyone see this? Okay. So now take 1 minute and see how you might be able to use these vectors to get back to the claim that we were trying to prove. Can you show that the demo that you just saw was not a fluke and there's actually something structural going on here? Talk to your neighbor. We have a couple of minutes. Don't leave anyone without a talking partner. The one is representing the just as a reminder, because I got this nice question, I have keep talking. How many people think they have some idea of what's going on? How many people want another minute to talk? Okay, take 30 seconds. 30 more seconds to think, talk, try and figure out what's going on your own. Okay. So what do I get? What do I get when I write out x1a1 plus x2a2 plus x3a3? I get, someone want to describe what they thought? What did they do when you added these three things? x1 a11 plus x2 a12 plus x3 a13, right? So this is the first element, right? These are all three vectors that have 3 rows and 1 column. When you add 3 vectors with 3 rows and 1 column, which is a 3 by 1 vector, add 3 by 1 vectors, you're going to get out a 3 by 1 vector, right? So the first component is going to be this. The second component is x1 a21 plus x2 a22 plus x3 a23, And then you have x1, a31 plus x2, a32 plus x3, x3, a33, right? And now what is a times x? When you do this matrix vector multiplication, what do you get out? The same thing, right? It's exactly the same thing. So what have you just proved? Have you just proved the claim by writing out this matrix vector multiplication? So even though we started out by constructing these matrices, thinking about the rows, turns out we can actually understand matrix vector multiplication not just in terms of these representations of systems of linear equations, but also as another kind of linear combination. When I think about the following, when I think about this thing, right? When I think about this equation here, I have three vectors, a1, a2, a3, and I'm weighting them with three numbers, x1, x2, x3, right? So what is this? This is a linear combination of the vectors a1, a2, a3. So what this is saying, what this claim is saying, is that matrix vector multiplication can be interpreted as a system of linear equations, but it can also be interpreted as a linear combination of the columns of A, right? It's the linear combination of the three vectors that make up these columns of A. These are two different kind of ways of thinking about this. So, any questions? I guess I have 1 minute left. I'm going to leave you with a question, since I have 1 minute. The question is, when I think now about these kinds of equations, ax equal to b, right? We've always been thinking about this as, can we find the x are the unknowns, so that we get this vector b. But when I think about it in this interpretation, what am I thinking about? Can I find every vector b as a linear combination of the columns of A? One is, do we have a solution for the system of linear equations? The second question is, can we find solutions, or can we find a linear combination such that the columns of B always will give, columns of A will always give us B? These two are actually very connected. They're the same question, and we'll talk more about this in next lecture where we'll pick up.